All right, today is our last day before spring break officially. I am going to follow, the schedule for spring break, so there will not be any assignments for over on Friday or the next week. Um, so I want to leave you with me going through an example for a somewhat complicated circuit. This should hopefully help you kind of figure out how to tackle circuit 10 and anything else that gets very complicated. Um, because even if I showed you some complex circuits on Tuesday, but even with you can kind of understand how those work. When you see something like this, it becomes intimidating in terms of figuring out like what the heck do I do? There's so much to look at. Like where do I even start, right? So I set up this circuit here. I base it off of this image that I found on Google, where I basically just assigned values to the resistors based off of their subscript numbers. So this one is going to have 1 ohm. This one's 3 ohms. I shifted this around very slightly. Like this 3 ohm resistor is up here, but it's the exact same circuit. Okay, there's nothing different. For some reason, there was no R2. I don't know why, but okay. So that's just what I'm going to go with. So what I'm going to do is I'm going to find, just like with the worksheet, the total current, the total resistance, and the individual voltage and current for all of these resistors. And I'll show you the process for doing this. The first step for any of this is to figure out the total resistance. And my best advice for this is sort of go from the inside out. Okay, so look at what kind of small pieces in here can I combine? And say, okay, these two can combine as a series piece. These can combine as a parallel piece. And as you sort of combine them to get higher values, or well, if it's parallel, it's lower value, you can sort of put them together and build your way up to looking at the whole thing. So the simplest thing here is that, well, this 3 and this 4 are in series with each other, right? I mean, there's an angle, but that doesn't matter. There's between these junctions, right? The current just goes through this, then through this. So these two are in series. So that means, let's see. Yeah, so I kind of wrote this down here. I can sort of add this. So I'm going to say the sum, just to clarify. So I'm going to say R34. That basically means the total resistance for 3 and 4, they're just in series, so it's just going to be 3 plus 4 is 7. Okay? So this piece here, this series branch, has a total resistance of 7. Now, this branch is in parallel with the 5. Okay? So, for example, I'm not going to do this because then I have to rebuild it all over again, but I could sort of replace these two resistors now with one 7 ohm resistor. And then this one 7 ohm resistor, for example, I could maybe just replace this one with a wire and then change this one to 7. That is now pretty clearly in parallel with the 5. Now, you might think, what about this 7 over here? Well, we can't do anything with that yet because you might think, well, aren't the 5 and the 7 in series? No, because you have this junction here. This junction comes in and it's different. And you might be able to notice, it's hard to tell, but the current you might be able to see here, it is a different speed here than here and then here. It's hard to see the difference, but it is faster here than it is here. So it's not the same. So no, you cannot treat the 5 and the 7 like they are in series. But you can treat the 5 and these two like they're in parallel. So this means that they're in parallel. So 1 over R345 is going to equal 1 over R34 plus 1 over R5. So we get 1 over 7 plus 1 over 5, which becomes, I'll just make this easy and just do be 7/35. And this would be, actually, wait, no, this one's 5/35. And this one's 7/35. That becomes 12/35. So therefore, R345 equals 35/12. That's not 12, that's 12, which is 1/12 less than 3, which, no, I don't know. I'll just freaking do the math. 35 divided by 12. Okay. 2.617. Did I say 617? 917. I can't type 917. Okay. I'll round to 3 decimal places for all of these. Okay, so now we have total resistance for 3, 4, and 5 is this. Okay. So that's this here. So this, all of this here has a total resistance of 2.917. Now this piece here, now that we've basically simplified this, in other words, we simplified these three together are now in series with the 7, right? No matter what my current goes through for either of these paths, they then have to go through the 7. So once I've simplified these three, these are now in series with the 7. So, therefore, that's going to be R3457 is just, it's in series. So I get 2.917 plus 7, so my total resistance for that is 9.917. Okay, so now I've gotten a total resistance for this entire branch. Now this entire branch is parallel with this, right? Once I can either take this path, or I can go this way, which then does something with any of this. And we already figured out that this in total is the 9.917. So this is in parallel with 6. Okay. So that means 3, 4, 5, 6, 7 is 1 over R6 plus 1 over R3, 4, 5, 7. So I'm going to have 1 over 6 plus 1 over 9.917. Okay, so this, I'll just do the math for this one. Okay, so that's the plus 7, there's your 9. Okay, so I want to invert this and then do plus 1 divided by 6. Okay, so that's my 1 over, so that's, I'll do 0.2675. Which means, now R 3, 4, 5, 6, 7 is 1 over 0.2675. So invert it again. Okay, 3.738, I'll do that. Okay, so now I figured out all of this. All of these right here. I figured out all of these paths equals that 3 number. And therefore all of these is now in series with the 1. Right? Because I pass through the 1, I have to pass through the 1, and then I do something with this whole thing. And again, I figured out this whole thing is, well, what I just figured out, the 3.738. So therefore, our total, which is R1, 3, 4, 5, 6, 7, again, there's no 2 for some reason, is just going to be R1 plus R3, 4, 5, 6, 7. Oops, I clicked the 2 by accident. Again, for apparently the number 2 doesn't exist. So then it's 1 plus 3.738. So my total resistance is 4.738 ohms. That is my total resistance. So now I can get total current because I have total resistance. I have the total voltage up here, 10. So V total equals I total times R total. So V total is 10 equals I total of, well, I don't know, that's what I'm solving for, times 4.738. So I total equals 10 divided by 4.738. So, oh, I have to let me add 1 to this. Okay, so that's my number there. So I'm going to, it's dividing by 10, but then flipping it. Get there. 2.11. That is my total current, 2.11 amps. So we have our total values. Let me make sure, let me just write this out here just so I have everything. V total is 10 volts. I total is 2.11 amps. And R total is 4.738 ohms. Okay, those are my values. Now I have to get the individual pieces. So let's think about this. Remember, we have to use the rules that we had. For the rules, it was that if things are in series, the currents are equal and the voltages add up together. If the pieces are in parallel, the voltages are equal and the currents add up together. So let's start with what we know. We know what the current is through the battery. So that means anything in series with the battery has to have the same current. But the only thing that's in series with the battery is R1, right? Because to get to any of these other ones, we have to cross a junction. And once we cross a junction, then things split up and it's different. So we don't know. But we know R1 has to have the same current as the total. So therefore, we know I1 must equal I total. So it's 2.11 amps. Now, since we know I1 and we know R1, we therefore know what V1 is. You can use Ohm's law. So we have 2.11 times, 1 ohm. So V1 is 2.11 volts. Okay, so we know that the current that passes through this resistor is 2.11 amps, and we know that the voltage used up to cross the resistor is 2.11 volts. Now, what this means is that once the current crosses here, it's now going to split up. Okay, now we don't know what these currents are going to be. We could do some things to figure out, okay, well, this current plus this current would equal this current, blah, blah. We could do that. But what we do know is that any current that enters this point here, any electron, well, again, the electron's going the other way, but any current that enters this point here, it must exit this point here. Okay, so what this means, again, it's going to take a different path, but whatever enters here must exit here. So what this means is that between this point and this point, the voltage is going to drop, and it must drop the same amount, because the current could just go this way. It could go this way, or it could go this way. We don't know, but since it could go any of those ways, it must drop the same amount of voltage. Now, we know the total voltage that's gained from the battery is 10. We know it must lose 2.11. That means no matter which path it takes here, it must lose the rest of that voltage to get back down to 0 voltage before it gains it back going across the battery. So, this means that, here I can kind of, what are our options for paths? We have just crossing 6, we have crossing 5 and then 7, and we have crossing 3 and then 4 and then 7. Okay, those are our options. So what this means is that we have V6, V57, and V347. Those all must be equal, because they're all the current has to go through one of these three options, and therefore it must lose the same voltage across all these options. But what is that? Well, again, the total is V10. It must gain V10. It gains V10 going across the battery. It then loses 2.11, so it must lose the rest of it for any of these three paths. So this must equal 10, or in other words, it must equal V total minus V1, which is 10 minus 2.11, which is going to be 7.89 volts, right? It's going to be negative, but yeah, okay. Ignore the negative, I'm just shorthanding this. So, now, this means that we have V6. Okay, we have V6. Again, then we have to figure out these paths by themselves. So if we have V6, we can then find I6, right? So V6 equals I6 times R6. So we have 7.89 equals, wait, let me get that off. Okay, there we go. Equals I6, what we're solving for, times R6, which is just 6. So, wait, I'm putting the equals, I don't want an equals. So that means I6 equals 7.89 divided by 6. So again, it's negative. Ignore the negative. I just shorthanded it. So it's 1.315. 1.315 amps. Okay. So we know that this path therefore uses up 1.315 amps. Now, what does that mean? Well, again, the amps coming in here, into this junction, was 2.11. Okay, so 2.11 amps come in. What comes out? Well, what comes out is you can either go this way or it can go this way. Now, therefore, we just found the current that goes along this path. Now, the current that comes into this junction, again, the total current doesn't change. So if I have 2.11 coming in and, 1.315 going this way, the rest of it must go this way. Okay, now then it splits up again, but notice here it comes back together to cross the 7. Okay, so what this means is that the 1.315 is coming in here, some other amount is coming in here, but then whatever these two come added together must get equal to 2.11 that comes around. So in other words, the current through 7 plus the current through 6 must equal the total current, because these two pieces are in these. Well, again, there's this stuff here, which we'll deal with in a second, but these two junctions come together. So the current coming through here plus the current coming through here must equal the total current going around. So I6 plus I7 must equal I total. So we have I7 equals I total minus I6. I total is 2.11 minus I6, 1.315. 0.795. That's my current through I7. And again, now that I have I7, I can find V7. So I have I7, 0.795 times 7. 7. I'll do, I don't know, I'll just do 5.565. Nah, I should be accurate, 5.566. Okay, there's my voltage. So, there's my voltage, crossing 7. Okay, now I have the voltage crossing 7. Okay, so let's take a step back now, and let's think about what we had. We got, okay, so now that we have a voltage, let's think about our voltages. So our total voltage is 10, and we found this drop was 2.11. That means I said no matter which path that the thing goes, you have to lose the same voltage. And that's how we got V6. Yeah, it's how we got V6 7.89. So this means if you go this way, you lose 7.89 volts. If you go this way, you lose 7.89 volts. And if you go this way, you lose 7.89 volts. Now, that said, though, these two paths, we don't know about the individual pieces of this path yet, but what we do know is that when you cross here, when you cross 7, you lose 5.566. So in total, if you go this way or this way, you lose 7.89, but if you cross this, when you cross this, this piece makes you lose 5.566. So this means whether you cross the 5 or you cross the 3 and the 4, you have to lose the rest of that. Okay? So this means V5, because you could just cross 5, must equal V34, because you could cross both of those, and those therefore must equal the number that we got before, the 7.89 minus V7, right? Because we know once you go from here to here, you must have lost 7.89. When you cross this, you lose 5.566. So the rest of it you must lose whether you go this way or whether you go this way. So this number ends up being 7.89 minus 5.566. So you get, I'm just going to, again, shorthanded, this is going to be a negative number, but that's okay. 2.34. Wait, 2.324. So this means whether you cross this one or you cross these two, you must lose 2.324 volts. Okay, so now that's V5. So now that we have V5, we can solve for I5. Okay, so so we have V5 2.324 equals I5, which we're solving for, times R5. So, oh, R5 is just 5. Oops. So, I5 equals 2.324 divided by 5. Yeah, and ignore the negative here. 0.465. Okay, so that is I5. Okay, but now we got a current again. So let's think about the currents we got. We have the current through 5 is 0.465. Okay, so when we cross here, our current is 0.465. Now we already have I7 also. What's I7? I7 is... Where's I7? This is I7. I7 is 0.795. So what this means is that when we cross here, our current is 0.795. Crossing here, our current was 0.465. So, but again, the current from these two adds into this one. So this current coming this way plus the current coming in this way equals this current here. So in other words, I7 equals I5 plus I34. Okay, those currents add up. This current plus this current equals this current. So, well, we have I7, that was 0.795, and we have I5, which is 0.465, plus I34. So, I34 equals just the subtraction of that, which, again, I can shorthand by doing adding. Okay, 0.33. So this means the current running through this branch is 0.33. However, these are in series, so that means the current that goes through this resistor must equal the current going through this resistor. It is the total, so therefore, even though, we have I34, yeah, but I34 equals I3, which equals I4. So now all that we have left, we have current, we have I3, we have I4. Now all we have left is V3 and V4. So V3 equals I3 times R3 equals 0.33 times 3. Well, that's just going to equal basically 1. I'll multiply by 3 to get like a specific number. 0.99. Okay, fine, I'll just do 0.99 just to do it. And then V4 is I4 times R4. So 0.33 times 4. So divided by 3 and then times 4. Okay. 1.32. So, what do we have? At the end of I think that's everything. We have V1. What's V1? V1, I got that right at the beginning, right? V1 is 2.11. Yeah, V1, 2.11. Okay. V3 equals 0.99 volts. Putting that by accident. V4 is 1.32 volts. V5 equals, where's V5? V5 is right. Yeah, 2.324 volts. Space here. V6 equals, where's V6? V6 equals 7.89. I know. I'll here, let me just move it on the next page just to make things clear, okay? I'll do it this way. Okay, and V7 equals V7. Where is V7? V7, 5.566. Oh, and we have that V total equals 10. Again, you might think, well, this does not add up to 10. No, it doesn't, right? But that's because it's not that everything is in series or parallel. It's all a weird combination. So you can't, we could work through it and figure out to make sure it works true by, again, going through the pieces, but I don't think you want me to do that. So I'll just, and now I'm going to put the i's in. So I1 equals 2.11. I3 equals 0.33 amps, which was the same as I4. I5 equals, where's I5? There it is, 0.465. I6 equals, I6, 1.315. I7 equals, where is I7? I7, 0.795. And then I total was 2.11. Okay, and then also lastly we had that R total was, I got that at the very beginning, which was there, 4.738. So, now's the time to check if I'm right or not. Let's bust out the thingies. All right, so first, let's, again, we want this one at this end, this one here. 0.21, that's V1. Okay, that 0.211, that was correct. Now V3 is going to be here. 0.99, that was right. Yep, V3, 0.99. Okay, again, there was rounding involved, so if I'm off by 0.1, I don't think that's wrong. So, yep, okay, so 1.33. So V5 now should be 2.32, or maybe 2.33. 2.32, okay, there you go. V6, 7.89, I believe that's right. Yep, 7.89. And then this one's going to be rounded a bit. 5.57, 5. Yeah, okay, 5.57. So yeah, there you go. So my voltages were correct. I did those correct. And I mean, I used the currents to get to those, so my current should also be correct too. But let's just make double sure. This should be 2.11. Yep. This one is 0.33. Yep, that one 0.3. This one also 0.33. Yep. 5. What was? I think so. That was the 0.46. Yeah. So again, rounding, and then this is going to be, let's see, 1.31. Yep, that's what that was. Right. Yep. And this should be 0.79 or 0.8. 0.8. Okay. So yeah, there you go. It all worked. I was correct for all of it. So there you go. You can hopefully maybe kind of see the logic for this. You're sort of breaking it up into pieces. Basically, you sort of start from the inside. This is sort of, I mean, it's not really the inside, but sort of the inside in the sense that like it's the most. You take the most sort of splits to get to this piece here, and you find this, and then you sort of work your way out to all of it to get sort of a total resistance. Then once you get that, you sort of then work your way back in, figuring out different voltages and currents that can help you kind of narrow in and figure out the numbers you need. So it is tricky. It's a tricky sort of process, but it's not because the math is hard, right? I'm adding and I'm multiplying numbers that are not even that bad, right? This is not difficult math in terms of like what you're doing. It's just hard to figure out what you're doing. And I don't know, I like this. I don't know why I like this, but I do. I like it. So yeah, hopefully you can kind of see maybe how this can come together. It's in terms of tackling stuff like in circuit 10, which is very tricky. I will be showing, I'll probably put a video up near the end of spring break. It's not going to be like a lesson where it's like, oh, here's the thing you have to learn, but I'm going to use to go over the worksheet to show how everything works and lines up, and that everything the answers are. I don't want to take like a day, over the next week to, the week after spring break to do that. So, yeah, that's I'll definitely show you how to do circuit 10 for sure. And then we'll figure out from there. I'll see if I want to do the rest of them. I don't know, we'll figure it out. But yeah, so hopefully this can help you going through this, seeing how this all works. And you can try to tackle some of this hard stuff with that. So okay, that's it for me. I feel accomplished. I did a thing. I got answers. Hooray! Hopefully you could follow this. This stuff is kind of hard to always show this way. Something that I like to do, especially for this first part where I'm finding the total resistances, is to sort of like replace the pieces of the circuit with sort of like equivalent resistances, but I can't really do that with this without breaking this all up and then I have to remake it. And then also, you can only increase or decrease resistances by like 0.5, which is kind of annoying. So I can't really be that specific. So, oh well. But yeah, so hopefully this is helpful. And yeah, you can work things out with that. And um, yeah, so see what you can do. Work together in the worksheet and the lab over spring break, and that's all. I'm not gonna be posting another like academic video that's like a lesson. Except I'll probably post something near the end of spring break about going over the worksheet. Um, but yeah, that's that. Now, in terms of the test, I should clarify this there because again, there is going to be a test on this unit, and the current plan is it is going to be after spring break. Now, I'm not exactly sure how I want to do it. Um, I know there's no way I can expect like people to not share answers and stuff. So I might just sort of accept that and sort of incorporate that into the test itself and sort of have like, here's a take home test where I expect you to be using your notes and expect you to be using each other to sort of figure things out. But if I were to do that, I would have to make it fairly challenging. So I don't know. I'll figure it out. I'll see what I can do, and um, you'll find out. So there. Okay, that's it for me. I'm finally done.